A couple of other things actually about Ahmer. He's going to talk to us about some of his work, and the nonlinear mechanics says some of it. But he's also chair of the London branch of the IMA, and you're also an editor of Steele, Maths Today, and 50 Shades.
That was one of the titles we got rid of.
50 Visions of Mathematics, which is a book that was published to celebrate. This talk's just going to go downhill, isn't it? to celebrate 50 years of the IMA. So I'm delighted to welcome Ahmer. Over to you. That sort of thing.
So I was only A of Sand Park. So I was probably the second A. Because Sand Park was the editor was called Sand Park.
Yes.
Yeah, so Sand was Steve, Alan, Marianne, Paul, Ahmer, Rachel, and Chris.
Chris.
There we go. And you can work out the surnames if you like them. Okay, so thank you for inviting and thank you for the invitation from these students. Right, so I'm going to talk to you today about some of my work on structural instability or buckling, and hence the title Buckliphobia versus or buckliphilia. So for those who have worked it out, buckliphobia is some people who are scared of buckling, and buckliphia is a sort of people who really like it. I'm sort of a bit of a schizophrenic on this one because and in my day job as a civil and structural engineer, normally we don't like buckling, we don't like things falling down. But for my nonlinear mechanics hat on, sometimes it's quite interesting. The maths is quite interesting, and the phenomena is quite useful as well. It can be. So I'll try and give you a flavour of both items today. Okay, so what I'm going to talk about, well, I'll give you a brief introduction of structural instability, some examples. Then we'll talk a little about equilibrium and stability. I'll try and get the equations down to an absolute minimum, so that it's the facts of the talk which are important, not really the mathematics in this particular talk. And it's also structural nonlinearities, which are absolutely key to understanding these behaviours and where these behaviours arise from. Some energy concepts, we'll discuss those. We'll talk about severity of instabilities, and then we'll talk a little about how instabilities interact, and then talk a little bit about some more research topics, focus topics on cellular buckling and shape morphing, and conclude. Okay, so structural engineering has a distinguished history in its own right. I mean, it's a subject in its own right, and it has its own literature, and of course we are working in a building, and that's a testament to structural engineering. But also, which you might not realise, it relies heavily on nonlinear maths. In particular, the nonlinearities come from either the material behaviour or the geometric behaviour. When we talk about geometric behaviour, we're talking about things that deflect a long way. Okay, so in particular, I'm going to discuss today geometric effects. I will talk about material behaviour a little bit as well, just to define what it is. But we'll be talking about geometric effects, in particular structural instability, which shows some interesting features, practical relevance, and prospects of it being exploited to your advantage. Okay, so Buckliphobia versus buckliphilia. Now, I can't claim that title is an original title. I actually borrowed it from Pedro Reis in EPFL in Switzerland, who wrote this very nice paper about 3 years ago in the Journal of Applied Mechanics, where he discussed a lot of different applications where buckling is being used to actually enhance behaviour. In this particular case, he's more looking at soft matter materials and looking at shape morphing applications. So not really into the structural engineering part, but more into the small scale part where the deformation actually from instability actually gives you something advantageous in terms of the behaviour in practice. Okay, so let's look at a classical example of instability. If you're a structural engineer, this is the one, it's the first thing you look at basically as an application, which is a column. So there's plenty of columns in this room here, there's one there. See, well, probably can't see many more because they don't tend to be exposed, but there's definitely one there. The building was supported by that, but basically under compression. Okay, that one probably made of concrete, but what we're talking about in structural instability is things which tend to be quite slender and thin, like steel, for example, which has normally much less volume than concrete because it's much more expensive. but it's also much more strong. Okay. Anyway, so here's some standard columns under compression. So if you apply a force here, there's some metal beams applied as a compression to this strut here, and this strut is buckled. You can see it moves sideways from the original position. If we change the boundary conditions, we get a different type of behavior. We actually get more load on the top there. If we, I think this one has a clamp condition at the end here, where it can't rotate, but it can rotate here. Okay, so that gives you slightly more load than this one, but less than that one. And then if we have a cantilever, which is free at one end, see this can slide here, then it can only take a very small amount of load before it actually collapses. Those of you who travel by train, you might, this probably doesn't happen in the UK very often, although it probably clearly does because it's a good excuse. But this is a type of buckling that occurs in railway lines where you get thermal expansion. Okay, so rails tend to be welded together these days. In the old days, of course, they used to have some expansion joints, but it's not very good for fatigue and things like that. So they weld them together. Now, normally they would put a big pretension in there before they place the rails, but if the pretension gets diminished over time, let's say, and you get a sudden heat gain, basically what happens is the rails try to expand. They can't expand because they're welded to the next rail, and they go into compression, and then they buckle. And it's quite a big force here. Look at that. These are railway sleepers, which are usually buried into the ground, and they've actually moved with the rail. So that's a massive force in there. So this is from the US, and there are plenty of pictures like this if you look at railway line buckling on Google Images, for example. I'll leave after the Google Images to find buckling of this type. This is a lateral buckling phenomenon, so going sideways. You can also get buckling upwards. Okay, this is outside. This is mechanical engineering at Imperial, and this is law school lines, at the back of law school lines at Imperial, and our department sort of over there. But this is a sort of wood decking here, which has uplifted for the same reason as this one. Okay, in this case, it was allowed to move sideways. It was the easiest thing for the structure to do. In here, the decks can't actually move sideways because they're all clamped together. Okay, so the best thing that you can do is move upwards. Okay, so this was on a very hot day actually, in May 2005, it's quite a while ago now. It was about 32 degrees that day. But about 4 days before, about 8 degrees. So there was a lot of temperature change in a very short space of time. There's me with hair, a bit slender as well, probably, back in 2005. And just showing here, there's a little shadow of this tank here. And you can see that the distance of that is quite high, and these are large deflections. Something in terms of these things, when we define it as large deflections, we think of deflections about the order of the element itself. So the decking elements would be about this deep as well, and you can see the deflection is quite of the same order. So it's all called geometrically nonlinear. So you can't make assumptions like sine theta is theta, and expect to get the same information that you would want if you wanted to model this to model large deflections. Okay, so these were examples of very simple instabilities, but you can have simultaneous instabilities as well. And I wanted to show you at least one video. I'll show you a few videos today. See if this comes up. Let me just pause it for a second. So this is a video taken by me. This is a third-year project that our undergraduates do, where they have to build an aluminium beam and test for failure. Okay, so it's a very simple setup. It's supported here. It's called simple supported beam. Which means it's resting here and it's resting over there. Okay, it's being pulled down here. So this chap here is turning this handle. This basically turns a screw, which pulls this down. There's a rod which is passed through the beam, and it just basically pulls it down. It puts it under what we call three-point bending. In other words, there's a big point load coming in the middle there, and there's two reaction forces at the ends. Okay? These 2 points here and here, these stop the beam from displacing sideways, and the students are allowed to put that wherever they like. And they're allowed to, within these, they're given certain sizes of plate and angles and rivets to put it together and design to a particular load. This wasn't a brilliant example, but they gave it a nice video. Okay, so he's about to, I'll just shut me up because I keep talking on this one. Okay, so keep watching this point here. So when he applies the load, this thing will start to fall and this thing goes into compression. So you start seeing a natural sine wave coming in, or something which is a modulated sine wave. Okay, and then what happens is the thing buckles, this will buckle locally and then it buckles globally. So you'll see that this thing will start moving, it'll start twisting and dropping sideways. There you can see, just pause it there. Okay, so you can see that the back looks vertical, but this one is at an angle. Okay, so you can see it's moved sideways as well. So this is an example of what we call load interaction. I'll just play the thing again. Okay, so in this case, the load buckling in the top flange there, okay, the thin plate at the top there, which I'm pointing there, then induces a global buckle into the main beam there, and this is called load interaction. Okay, it's a nonlinear interaction between the local buckling mode and what we call the global buckling mode, which in this case is a combination of lateral deflection and twisting. Okay, so the global load was lateral torsional buckling, which appeared at the end. Plate buckling occurred at the beginning. This is what we call local buckling as well. And this is an example of node interaction. We'll return to a similar problem later when we look at some actual work that we've done at Imperial. Okay. So, what we're going to describe is research into structures with your buckling. So, static systems are analysed. We can analyze it from formal use loss of motion, or we can actually, what we tend to prefer in structural systems problems is to use variational principles or potential energy principles. It's a static problem. Okay? So potential energy is often used in analysis. So here's total potential energy here. It's a function of two things in this case. It's a function of the applied loading and the generalized coordinates which define the kinematics of the system. So this can be decomposed into the strain energy, elastic potential energy stored in the structure, and the work done by the external loads. Okay, so that's everything defined there. So Qi is the generalized coordinate. We'll be plotting that against P, the load, quite often, and that's called an equilibrium diagram. We'll come to that later. Okay, so potential energy principles are as follows. So we have stationary potential energy due to equilibrium, and minimum potential energy due to stable equilibrium. Okay, so that's some well-known energy principles. And if we plot the energy function, any function V, let's say it's a function of just the kinematics for the sake of argument, and we plot the one of the generalized coordinates here, and we get a curve. So this is just an arbitrary curve here. The starting points, the stationary points here, define all the equilibrium states. Everything else is not an equilibrium, okay, by definition of the first principle. We can actually think of this energy function as a surface, as a physical surface. Okay, so let's change V to Z, this vertical coordinate, vertical displacement coordinate, and let's think of it as a surface with a ball on it. Okay, so number one, this local minimum here, if we put a ball in there and we perturb the ball, it just sort of jiggles around here. So this is defined as a stable equilibrium. It's just an 8 memoir. So that's a stable equilibrium. This is an unstable equilibrium because if we perturb the ball here, it would just go off somewhere and find another equilibrium state. Number 3 is also an unstable equilibrium, even though if we perturb it to the right, it would want to come back to the left, but then it would fall off and go off somewhere else. Okay, so case 1 is stable, case 2 is unstable, which is the maximum. So case 1 is the minimum, case 2 is the maximum, and case 3 is a point of inflection. And a point of inflection actually also defines what is a bifurcation point. In other words, where the surface has a locally flat profile. In fact, its second derivative is actually vanishing of the actual function phi. Okay. So that's by the way. If we have more than 1 degree, so this was for 1 degree of freedom, okay? we have more than 1 degree of freedom, we would end up with a surface, a proper surface here, a 3-dimensional surface. So we have a local minimum, local maximum, that would be stable, unstable, and we could have a saddle point, which is unstable as well, because it's maximum in one direction and minimum in the other. So, the ball, as it were, would want to fall off the maximum point. Okay, so the Newton's laws of energy principles lead to equilibrium relationships, and these are very usefully plotted as equilibrium diagrams. So basically, plots loads versus deflection quantities, and the combination, the curve defines the combination that satisfies equilibrium. Okay, this diagram also shows structural strength. Okay, the ultimate load carrying capacity, which is useful if you're designing a structure, and it shows the structural stiffness, the resistance to deflection of the loading. So here's an example. Okay, so here's loading P against displacement Q. Just a random example here. So let's say we have a column which is being displaced. It's compressing by amount Q, as shown here. So Q is non-zero, and let's assume it's nice and elastic and linearly elastic. Okay, so we have initially, starting from zero load, we have a rise of Q, as sort of shown here, and then we reach this point. This point is called PC, the bifurcation point, or the critical equilibrium state. This defines the onset of any buckling instability. Okay, beyond that, we get, so before that, so we start at zero load and end up at this point here. This state is known as the pre-buckling state, sometimes known as the fundamental state as well. And all of these states are in stable equilibrium. Okay, after this point, we have a stability of post-buckling state, which might be stable, might be unstable. This one would be stable up to this point here, but we'll not go into too much. But basically, you have a post-buckling state, and you might get collapse at the end. Okay? So what I'm saying here is that it's indeterminate. This stability of this is indeterminate without further analysis. This part is always stable, but this part might be stable, it might be unstable, but we can only determine this from if we do some nonlinear analysis. Okay? The slope of this curve, by the way, gives you the stiffness. So dP by dQ gives you the stiffness at any point on this particular graph. So you can see it's positive here, it's smaller value, so positive large values, positive smaller value, and then it's negative here. And this point here defines the strength, PU, the ultimate load. So the analysis of instability can be divided into two parts. First of all, linear analysis, which is to predict when the instability is triggered, this onset point here. That would give you this point, but nothing else beyond that. Okay, so that is when stable equilibrium becomes unstable, or the spark becomes unstable. Second analysis is nonlinear analysis. This predicts what happens beyond the initial instability. So this latter one requires nonlinearities to be considered as you might expect for this analysis. So where does nonlinearity come from? Well, nonlinearity can be in structures. They can be grouped into two broad categories: sources from the material or from geometry. Okay, from material behavior, we have stress-strain relation, the so-called constitutive relationship or constitutive law. So that plots relates stress, which is proportional to the applied force to a material, against the strain, which is proportional to its deformation and its displacement. So the simplest behavior is elastic. So when you let's say an elastic band, you stretch it and you let it go, it comes back to its original shape. In that case, you have no permanent deformation. If applied force is removed, then there's no memory of the deformation that it has been endured. And if we assume that the material obeys Hooke's law, where the stress is directly proportional to strain, then we can simplify matters quite a bit. Structural steel is actually a good example of something which behaves very much like this. Lots of materials don't. They have an elastic behavior, but they don't have a linear elastic behavior. Structural steel is quite well behaved in that way. If we take a structural steel stress-strain law, it looks something like this. This is the elastic range. It's very narrow in terms of the amount of strain. Okay? But it has a very high rate of increase of stress. The slope of this thing is given by the material, what's called Newton's modulus. Okay? So once the material goes once it's in this range here, or while it's in this range here, we can apply the load, remove the load, and it has no permanent deformation. But note that the elastic range is quite narrow, and this range can be nonlinear. Okay, so if you had an aluminium rather than structural steel, or if it was stainless steel, different alloy of steel, they would tend to have a curve more like that, more curve shape like that, rather than a straight line. Okay. Beyond this point here, where it yields, so this defines the elastic limit, basically, we start getting nonlinearity. So the materials can be overstressed, and from this point here, there is permanent deformation. You will still recover the elastic part, but you will have permanent deformation enduring in the structure if the stresses, also if the strains go beyond this particular value here. Okay. So there's three ranges here. We have the plastic plateau in steel. We have a region of strain hardening where the stresses increase. And we have, well, after the point of maximum stress, we have the onset of failure. And eventually fracture, the whole thing snaps. Okay. So the material is fractured at the end, and the whole thing snaps up. We're assuming here there's something under tension. In terms of structures, what do we mean by geometric nonlinearity? So here's a plate, okay, just a cartoon of a plate here, with a defined deformation here. So this is W is a lateral deformation. Let's say that this thing has a very small thickness. Okay, if we wanted to work out what the strain was in this plate, it's defined by the in-plane displacement, which is U. Yeah, okay, you can see that U there. Okay, that's the first partial derivative vector x. And we have a second term, which is relating to the outer plane displacement, which is given by this expression here, half the dw by x all squared. So the first term here is to the power 1, okay, so it's linear. This is to the power 2, so it's quadratic, and therefore it's nonlinear. So because the deflections normally start from 0, it's probably perfectly flat to start with, this term will dominate first, and then once w becomes relatively large, this term will start to dominate. So this nonlinear term is only significant for large deflections. And it's this term here which will give you the information for what happens after buckling is triggered. Okay, so just going back to linear analysis. So systems simplified to small displacements, you can only establish the critical buckling load known as PC. So if we look at the equilibrium diagram here, so we have load P and deflection Q. So before any buckling occurs, now the deflection now is a lateral deflection rather than the vertical deflection. So initially we get a pre-buckling path which is straight up the p-axis. Okay, because there is no deformation theoretically for a what's called a perfect system before it buckles. Otherwise, it would have been buckling. Okay, so once it does start to buckle at the onset of this load here, PC, we get an increase of this displacement Q. Now, show Q deflect to the right here, that defines a positive value. If it deflects to the left, it will define a negative value of Q. It's just a measure of amplitude. However, because it's linear analysis, what you get is a post-buckling path which is perfectly flat. Now, in reality, of course, that's not true. So this can be very misleading. The flat post-buckling path is purely an artifact of this linear assumption. So we've assumed small deflections, so therefore we can only get the value of the critical load and nothing else beyond that. Okay? You might think that's fine, at least you get some information, but the problem is that some systems behave like this, like columns. Okay, so they do behave like this, but other systems behave completely differently. Okay, they have qualitatively different post-buckling paths. So nonlinearities control whether the component is stable or unstable after buckling. This sort of implies that it's sort of neutrally stable. So it uses stiffness, but it can hold the particular load defined at PC. In reality, we get something like this. We could have stable post-buckling. For those of you who are au fait with bifurcation theory, this is a supercritical pitchfork. Okay, so we have the fundamental path, the pre-buckling path here, which is stable, and then we have a bifurcation point, and then we have a post-buckling path where the path is above the critical load PC. Here's an example of system that behaves like this. So we have a load here, this is a rigid link system here, and we have a rotational spring of stiffness C. Okay, and this would be the rotation here, Q. Okay. In reality, and in real systems, a plate, a web in a beam like so would be very stable in post-buckling, as would the flange like we saw in the video earlier. Okay, so in this type of system, we have an increase in load capacity after instability. So the system can carry on taking more and more load after the instability is triggered, even though the stiffness has dropped, but the stiffness is the slope of this curve. And the post-buckling has gone beyond the critical load, so it's good for people who like buckling, good for buckliphiles, as I said. And also, we find that the another feature of stable post-buckling is that the deformation shape tends to be distributed or periodically distributed through the length as well. That's one of the signatures we can spot if we see something that is periodically distributed. We know pretty much that it's going to have a stable post-buckling profile. Now, these can actually fail once the material fails. Okay, so the stresses and strains get very large in these large deformations, and eventually they require the yield stress, as shown earlier, and then you get failure. But in the elastic range, they will just carry on increasing load. Conversely, we could have an unstable post-buckling response. This would be a subcritical pitchfork bifurcation. So pre-buckling path same as before. Here's the system. This time, instead of having a rotational spring here, we have a longitudinal spring, and that changes the behavior substantially. Now the post-buckling path goes downwards. All the nonlinear behavior is below PC, hence it's called subcritical. There's a reduction in load capacity after instability. During post-buckling, the load is less than critical load, and this is good for the people who are scared of buckling. Okay? And a typical example of this is cylindrical shell. It's a very well-known example. We've studied very, very extensively because it has this rather unstable behavior, and it's very difficult to predict its actual failure load to any degree of accuracy or reliability. Another feature of unstable systems is that, unlike the stable systems, which are nicely distributed in terms of deformation, these are very much localized. Okay? Although the cylinder has a sort of periodicity along the circumference, it has a very much localized deformation along the length. This is loaded under axial compression. Okay, so a bit like standing on a coke can. But it's not a coke can. That's not a size of dustbin. Because that's in my office. So I know how big that is. It's about that diameter. Okay. So what we've talked about so far is systems which have a pre-buckling path, basically, which is up the p-axis where no deformation occurs in terms of lateral deformation before any buckling occurs. So what we call those are perfect systems. What happens if you have an imperfection? So we've neglected them so far, but imperfections obviously exist. So manufacturing and fabrication defects. You know, if you're making steel, it cools at different rates in different parts of the steel. Therefore, it doesn't actually. It might be as straight as you have a manufacturing tolerance, but it will have some sort of arm of straightness. It's just a straight element. It's supposed to be a straight element. If you're joining things together, you weld things together. If it was a metal, and then you get heat affected zones, you might have holes in them for connecting them with other elements and so on. And you might have more concentric loading. Here, we've assumed everything is sort of axial, what we call, in other words, the load is applied perfectly along the center of the axis of the initial shape where, in this case, Q would be 0. Okay, so these imperfections can be included in relative ease, and they actually change the equilibrium diagrams quite substantially. So for the stable system, in fact, first of all, the imperfect parts are asymptotic to the perfect parts. So you can see here, it's asymptotic. This is the imperfect part, the perfect part of the stable system, and similarly for the unstable system. Okay? So for the stable system, it can be loaded as I sort of suggested before, the imperfect path goes past the bifurcation point, okay, and carries on loading until the material is overstressed, and then it will actually stop and will then curve over and fail, become unstable. The unstable system actually goes over a maximum well below PC. And if I have cylinders, it can be the PL value here could be 20% of PC. Okay, and that's for a very good cylinder. Okay, so they can be very, very shockingly severe in terms of the effect of those imperfections. The unstable system fails in the elastic range before it reaches the bifurcation load. Epsilon, by the way, is the imperfection size, and that's the initial offset of the model that we showed earlier when the loading was first applied. Now, if we plotted, so just going back to this one here, if we plotted a locus of the this limit point load against the corresponding imperfection, we end up with a graph that looks like this. This is PL over PC, the limit load divided by the critical buckling load against the imperfection size, and we get a 2/3 power law for this type of unstable system. So 1 minus alpha. Alpha is just a constant which relates to the particular system that you're dealing with, and 2/3 power law isn't a curve fit, it's an actual mathematical law that you can it's a power series law, so you can get other terms in there if you increase your analysis, but to reading order, that's the term you get for this type of system. So the actual capacity drops away very, very quickly with the imperfection. And there are different power laws for different types of system. So just need to do the analysis of that, just an example. Okay, now we looked at very similar instabilities so far, a stable and unstable system. There's also an asymmetric system which I don't want to go into, but that exists as well. But is stability fixed? Let's consider 2 further questions. Can a stable system be destabilized while it's elastic? And if yes, is it potentially significant? Okay, well, I hope you can probably say that one is going to be yes, and so it will be very boring talking if just no, it is. Anyway, let's illustrate this. Let's consider something called a column. Okay, so this is a column here. Okay, so we've seen this a few times already before. So asymmetry means it's free to rotate here and here, and it's free to displace vertically here, and its load is directly above the support here. Okay, so this may buckle in an infinite number of ways, infinite number of ways. I'll say ways again. Ways. And we're actually an infinite number of waves as well, but that's one. But when it's unconstrained, it only buckles one way. So let's have a look at a movie. Okay, so this is one of my students who's very kindly. You can see actually in the background there with my striped shirt on. Okay, so what he's doing there, he's applying a load. In this case, it's actually fixed at the end, so it's capped at the end. So if we want to look at where the supported bits are, it's basically from here to about there. So what he's doing is applying a displacement here rather than just putting a massive force on there. So you've got a screw jack here, basically. And he's turning the handle, and the thing basically starts to buckle. And it will always buckle in the same shape here. This should be a full sine wave in this particular case, but because it's self-wave, it's quite a lightweight structure. It actually, lightweight and slender structure, it actually is affected by self-wave as well. But yeah, so it should get basically a full sine wave for that particular case. So it's like I'll just play it again. Okay, so he's going to load it up. You'll see it starts to bubble. And then we take the load off, but it's still it's elastic. In fact, he stops about 1 second before he should stop, and then I told him to carry a bit more than the movie stops. There you go. I'll start again in a second. There you go. It's bad directing from me. There you go. Okay, so that buckles one way. So probably an interesting video. And the equilibrium diagram for that would look an extract of the equilibrium diagram would look something like this. So you have zero load here. This is the fundamental, the pre-buckling part, fundamental part, and you have the first bifurcation where you have a critical load, and this would be the shape. The second bifurcation, we have this would be half sine wave, then you have the full sine wave, 3 half sine waves, and so on. And this would go on forever. But if you're starting from zero load and zero deflection, the first thing we encounter is this first bifurcation here, and it will buckle in that way all the time. Okay, it's a bifurcation, so you can have deflection to the right or deflection to the left. In a perfect system, it has equal probability. So all modes are distinct, so they're nicely far apart in terms of load, and they have stable post-buckling responses as well. So that's fine. Let's consider a slightly more constrained column. So let's put a spring at the middle of this support here. So this is connected here, it's free to rotate at this point here, but there is a spring which is connected to some sort of external support. So when this thing deflects, it compresses or tenses the spring. Okay, now, there's a possibility that if we have load 1, which was this thing here, this will be constrained now at the grid span. So there will be a resistance to that thing deflecting at the span. It might trigger mode 2. It might even trigger mode 3. Let's have a look what it does on the video. Pause it there, right? Okay, so now my student has grown another hand. And he's going to apply the load again, but this time we've got a very, very high-tech pen to stop it from moving. So this is effectively, from that diagram we had there, we had K was the stiffness of the spring. This would be effectively the K being infinity, but large, so that there's no deflection possible at the span. So let's go ahead. Let's apply the load now. So by introducing the constraint, we've actually caused the mode to change. Now there will be a point where that value of K is sufficiently small for mode 1 and mode 2. This is what we call mode 2. Let's take things off there and it suddenly jumps to mode 1. If we have a particular value of K where the critical buckling load for mode 1 and mode 2 are identical, or very close. Okay, so that's basically what I'm trying to get at. So depending on K, PC1, the critical buckling load for mode 1 may become higher than the one for mode 2, and therefore that would become critical. And this would become a higher mode. So in other words, here, this would basically swap around. What happens if the two critical buckling loads are the same, or very similar? This is a cusp of the mode change, of the buckling mode changing. And the post-buckling can be adversely affected if mode 2 is triggered in the presence of mode 1, or vice versa. Okay? So post-buckling may transform from stable to unstable. And these secondary instabilities are likely and causing mode interaction or so-called interactive buckling. So if you recall question number 1, can a stable system be destabilized by elastic? Yes. If yes, how come? And it's potentially significant through mode interaction, and of course it depends on the system. It could be dangerous if you don't want buckling, or it could be good if you want buckling to occur for whatever application. So just to explain what's happening in mode interaction, just another sketch here of an equilibrium diagram. So this is loading. Now we have two. Mode interaction, of course, requires more than one node, so we now need 2 degrees of freedom. So we have Q1 and Q2 defining the size of mode 1 and the size of mode 2. Okay, so let's say we have a stable post-buckling mode in Q1 only. Okay. If we have something which is destabilized by a secondary interactive mode, okay, we could have a secondary instability occurring. So let's go back a second. So we have 0 load, we apply load, we get to bifurcation, and we have a post-buckling path, which might just be triggering mode 1. But let's say we're having a secondary instability, which is triggering a second mode, which is a mixture of mode 2 and 1. This is just a shadow of this thing here. Okay, so it reaches here, let's say it follows this path now, and then hits a secondary instability, we'll call that second bifurcation S, and now it follows a spread path, either here or there. So now, instead of just buckling in mode 1, it's now buckling in a combination of mode 1 and 2. But, worst thing is, the load is dropping off. Okay, so load carrying capacity is actually reducing. Now, what happens if this critical bifurcation and this secondary bifurcation go less, is that you can end up with a very, very violent collapse. Okay, it's possible that the limit load here, as defined, this is the imperfect part, as it were, could be much, much less than the critical buckling load here. And this is what happens in the cylinder, effectively. Although there's not just two modes interacting there, there's lots of different modes interacting at the same time. Okay. So if CNS coincide, we have the possibility of instant particle collapse. And these are the sorts of things that give nightmares to structural engineers and make them buckliphobes. So some practical mode interaction problems. So ones where local and global buckling modes interact. So my PhD was on sandwich structures. There's a couple of samples from some experimental work that I did. Then, more recently, we looked at work on thin-wall structures. Next, that picture from that beam again, that movie again. This is a beam in bending. This is a beam in compression. This is not ours. This is a photograph from colleagues of mine in the University of Sydney. This is Professor Peter Mattinson and Dr. Jürgen Beck. And it's Jürgen Beck's PhD project. It's a stainless steel I section, just under compression. Okay? And we see here the flanges, both flanges here, and the web buckling under compression. And finally, we look at, we won't actually discuss this in this particular talk here, but look at interaction between global nodes as well. This is a cable-supported column. Yeah, these cables are pre-stressed. Basically, what happens is that you get an external support in the middle here, and it is very much like those two videos I've just shown you, where you've got an external support stopping the midspan from displacing. So, normally, as structural engineers, we're very fond of numerical methods, particularly the FE method. Okay. However, the FE method is not great for instability problems. Although the FE is brilliant at pre-processing, meshing, and post-processing, all very good. But if it has a nice, smooth response, then it's fine. If it has a discontinuous response, like bifurcation, like there, it can be quite awkward to use. You can get around these things by introducing carefully sort of crafted imperfections to get the behavior that you're expecting, but it's a little bit unsatisfactory. So the question then arises, we put in some sort of imperfect behavior, which coexisting equilibrium states after buckling are practical? And it's less obvious when we have these mixed mode interactive buckling problems. Okay, so solving my FE for the imperfect structures analyzed, there's a problem with another problem is it's quite inefficient in terms of the study, because you have to then consider all different combinations of imperfections that you might put in. And if you're slightly careless with your selection of imperfections, it may result in unsafe strength predictions, which is not good if you're a designer. So if tractable, analytical modeling or mathematical modeling for these types of problems is preferable for several reasons. First of all, you can solve a perfect system in the nonlinear range, which you can't do very well in the FE methods. There are FE methods which people are developing, which are getting around this problem more recently, but they're still not widely used. Okay, so we solve the perfect system in nonlinear range, and then you can infer the imperfect response as the bounds are known, because we know that the imperfect response are asymptotic to the perfect response. And they're usually quick to solve, and therefore it allows you to study lots of different combinations of, say, geometries, and allows focusing on more time-consuming FE analyses. So, modular structures, of course, can lead to highly complex sets of nonlinear equations. Algebraic equations for discrete systems or differential equations for continuous systems. So what we tend to have used is the appropriate numerical method to obtain quantitative results. If we have a series of nonlinear differential equations, we've tended to use the numerical continuation technique in auto, sometimes in MATLAB as well, and if we have algebraic equations, we sometimes use our even symbolic computation package. For model validation, we've used the nonlinear FE code APCUS, and if we have the funding, we sometimes do experiments as well. Okay? I quite like experiments, so they're good fun. Just looking at sandwich structures. So sandwich structures are lightweight components comprising two stiff face plates and then softer core material here. This core material is usually something like foam or a aluminium honeycomb or something like that, something which is mesh-like or foam type, and this is a solid, normally something like a steel or aluminium plate, or maybe even a carbon fiber composite. And they're only glued together, or they are welded together if they were aluminium, but less common. Okay, so they're applied in various different things, particularly in lightweight structures like aircraft and satellites. Sometimes they're increasingly used in bridge decks as well, where you have very long spans and you need a minimum weight. They're often used in cladding on buildings and in floors. And they're often used in sports equipment as well, because where weight is very much of an issue and packaging. So skis, for example, are some structures themselves. So faceplates can be considered as two structures by a core. The core provides the separation of the plates. So effectively, if we don't have the core, then this thing just behaves like a very thin strut. By putting the core in there, it behaves like one structure. And the depth of the structure gives you the extra stiffness. Okay, the separation of the two things, the two plates, gives you the increased strength and stiffness. So the panels can buckle globally, and the faceplates can buckle locally, and in combination, you get this interaction. So here's a sequence of 3 pictures here. So this is one of my experiments from about 20 years ago. Okay, so this is being loaded in compression. Okay, so it's just exported here. This is an aluminium faceplate here, rubber foam core material in the middle there, and there's a faceplate in the back there, which you might be able to see from there. Okay, so apply the load, no buckling, linear elastic response. Delta now is the vertical displacement here. Okay. We apply, when we apply the load to such an extent that it buckles, we have a critical buckling load here. This is the critical bifurcation, and then we get a modest. We don't get much rise in the load. Let's say it's completely flat, we'll say the bargo, but basically it buckles in this half sine wave. And then we get secondary buckling, we get a thinning here, we get global buckling being triggered with the global buckling, and then we get a sudden drop off in the load. So C is the critical bifurcation, S is secondary bifurcation. And we look at different cases for those particular geometries. So in terms of modeling this thing, so the global load is very well known to be a half sine wave, so we impose that as a condition. Okay? And this allowed us to change our, or to simplify our model such that it became tractable mathematically. So to calculate the total energy in this thing, we need to calculate the spin energy stored in the local and global forms for the bending and direct strains in the face plates and the direct and shear strains in the core. Okay, so end up with a quite long expression. And the work done by load, we minimize the total energy, we get a series of equations in particular things. So we were in these particular quantities here. So we have the outer plane displacement of the faceplate here, okay, shown there. Okay, we have the in-plane displacement of the faceplate. It's not easy to see that in the picture, and we have the end displacement. And we end up with a fourth order nonlinear differential equation in W, a second order nonlinear differential equation in U. It's all really differential equation. We assume what happens. It's a 1D problem. Things are not really happening in that dimension. It's just basically cylindrical buckling. And we have integral equations for the imposed load contribution. This is just purely a function of the fact that we're imposing this half sine wave as the global mode first. So behave for a given cross section. We have global buckling dominates for long length panels. So we make a very long global buckling would occur, and local buckling would really occur. If we made it really short, you have local buckling only and no global buckling. But if we made it for an intermediate length panel, you get this interaction quite strongly. Okay, so this is just a couple of graphs here. This is showing the solution of the differential equation involving with load. So this is the local buckling mode here. Okay, so it's completely flat. This is the total length, and this is the load dropping off. It's an unstable behavior. So as the load drops off, the deflection increases. This is W, the outplane displacement of the plane. This is U, the in-plane displacement, and this is the snapshot from Abacus from the finite element model, showing the faceplate here and the faceplate on the other side and the core material as well. The comparisons between the two were very good. As we decreased the load that came from the critical bifurcation, we ended up with better comparisons between the black line, which is the analytical model, and the FE, which is shown in green. Okay, so this is near the bifurcation point, but as the deformation increased, they actually converged very nicely. So it goes A, B, C, D, so that's the sequence. So it's actually comparing very well in terms of the wavelength and the amplitude of the buckles. And more importantly, or as importantly, is the equilibrium diagram. So this is load against the end displacement. Again, the black line is the analytical model, and the green line is the theoretical model, and the maximum is shown very well, and the post-buckling stiffness is shown very well. So very encouraging results. So further work on this has been done. How do you time?
Maybe just over 5 minutes.
Right, fine, I should be okay. So we have extra comparisons obtained for quantitative from different relationships. I'm not going to go through any of these, apart from the fact that the latter one here, nonlinear core relationships, led to this thing called cellular buckling. That's what I'll talk about next. So snaking or cellular buckling, which is essentially the same thing. The mathematicians like to call it snaking. We call it cellular buckling because what happens is effectively what you have is a sequence of buckles triggered in cells. So we have, this is a cylinder. This is work by Lord, Chapman and Hunt. So Alan from Bristol, Greg Lowe from Herrick Watts and Charleston from Bath, my supervisor. So this is an initial buckle of a cylinder. If you apply the more end displacement, you end up with the second row of buckles, apply more displacement, we end up with 3 rows of buckles. And this has manifested itself in sort of snapback. So the first bifurcation here is with a big snapback, and then we have a second snap with the second cell and the third cell and so on. So this is an example of a system which destabilizes, and you see it goes up and comes back down, and then it restabilizes, okay, it comes back up again, and then it reaches up to the material fails. So each cell here, each one of these snapbacks, introduces a new cell with localized deformation, shown here, known as cellular buckling or snaking. Now, this is an example where you can use buckling to your advantage. In, for example, mechanical engineering, the crumple zones that you have in cars, which absorb energy, basically trigger this type of behavior. And if we just simplify that picture there, we have this up and down behavior of the equilibrium diagram. And each cell here is associated with an amount of energy. That would be just the integral between this point and this point here would be the amount of energy that needs to be triggered, that needs to be absorbed, also it needs to be overcome before it buckles. Okay, so this would protect, say for example, the passenger from an impact. Okay, you would have that amount of energy, that amount, and that amount, and so on in sequence, and that can be used to your advantage. So this is an example of instability being used to enhance performance. So sequential instability may be good for the old Buckley files, even though it's nice and unstable for Buckley folks. Okay. Then we found this also in thin wall beams. I'll just run through this very quickly. More conclusive evidence found in thin wall I-beams. Okay, so this is under bending. It's a test system here. Here's the beam being tested. This is the test setup. The beam is under 4-point bending. This is the load here. The load here pulling it down, and so on. We found some this thing buckled globally, then it buckled locally, and then it buckled locally once more. So nothing was found. Similar type of model, 4th order differential equation with the 2nd order differential equation, the arc plane and the independent displacement as before. Numerical solution in auto again does the mode versus displacement and the amplitudes and the deformed shape. So here's the equilibrium pass. We have these snaps shown here. This is mode against lateral displacement. This is arc plane displacement amplitude against the lateral displacement. You can see the snaps here. Up and down, up, down, up, down. So we have destabilizing, restabilizing, and so on. Here's the deformed shape. This is a solution from of the differential equations mapped out onto the beam in MATLAB. So this is not an FE model, so we have the beam under bending, then it buckles globally, and then the local buckles, just watch here, local buckles build. In sequence, the wavelength of the buckles tends to reduce as well, and we get this type of behavior. And we get good comparisons with experiments. Sometimes we get persistent experiments, which means that we get a slightly lower value in the end of the experiments for the test here. So the modeling approach has been used for other thin-wall components, I-sections. Starts this with a beam, so it was on a bending, going under compression, that one there. We have stiffened plates, which are very commonly used in bridges and in planes, in plane wings, airplane wings. Rectangular hollow sections, and more recently we've been looking at angle sections, and they are very awkward to do because they have a very, very nasty habit of having the centroid and the shear center in critical locations. So it's not really nice in the model. Okay, finally, just to wrap up all this, so cellular buckling also appears in natural structures as well. So this is it's not Bude, it's a middle haven in Cornwall, quite near Bude, north coast of Cornwall, where it has this very chevron fault. We did some work a long time ago now, looking at what happens if you take layers and compress them. So if we, what's shown here is a load of paper. We've got two foam layers here, which are laterally compressed, laterally strained, and then we apply an axial load here. We first get what's called a peak band, which then propagates, and then propagates all the way down. The things broaden, bands broaden, and then join together. This is all one experiment, showing different stages. And we end up with something which looks remarkably like that. Here's another experiment with a much softer, this is quite a stiff boundary here. If we have a much softer boundary, we get something quite slightly different, which is when there's a parallel fold. Okay. Now, the thing about these folding behaviors are that you get these voids forming, and these are places where the geologists would want to search for precious metals. So when we get folding and we get voids forming, there are crucial locations for precious metal deposits or mineral deposits. Another example where buckling is good, or actually is a positive thing rather than a negative thing. And this nonlinearity is the discontinuous nature of the friction between the layers and the large rotation of the layers. Here's an example of, this is probably almost my final slide now. So this is a colleague of mine in Bristol, Ahmer, who showed me this nice picture here. So I've got a video of this. I've silenced it at least. It's got some. So what this here is a flap, which there's this in a wind tunnel here. So when the wind is applied, okay, so by increasing the airspeed, the monostable inlet snaps into its closed state, and then when you reduce the load, I should say back by the way, it opens up again. Okay, so this is an example of using. I'll just show you again. So there's a lot of air going over here. As the airspeed gets to a sufficient value, this thing closes up. And when the airspeed reduces again, it opens up again. So this thing is nice and elastic. It doesn't get damaged during this deformation, so it's buckling used to your advantage again. Okay, so the typical equilibrium diagram for this would be something like this. So here's the airspeed, which is proportional to the force and the displacement of the flap of the inlet. So this is showing the open region, the sort of transition region where the thing is closing, and this is where it's closed. This is the equilibrium path. So as the airspeed increases, so we have it increases here. Once it reaches this point here, this is not stable anymore, so it has to go over here. Okay, so there's a dynamic transition from open to closed. And then, as the airspeed, if it's over here, it's closed, the airspeed, and it reduces. Then it comes down, all the way down here, and then there's another dynamic transition from close to open. Okay, so there's an idea of what we call instability, I suppose. This is where shape morphing can be introduced from buckling. Another example of helpful instability. So nonlinearities, so some conclusions. Nonlinearities need appreciation. It's key to understanding structural failure. Geometrical nonlinearities govern structural instability, but not all engineering instabilities are catastrophic. Stable elastic systems have residual strength. An unstable system can be also exploited through the cellular buckling phenomenon or this sort of shape morphing structures from, and there are various other things which I'm not mentioning. Buckling can also be found in actual phenomena, and then again, and there it can be used in a positive way as well. And finally, mathematical modeling, variational calculus, and dynamical systems are all highly relevant to this type of research and actual practice. So acknowledgements, so just to acknowledge some of my colleagues, Vera Gardner was a very close colleague of mine in Imperial, and Giles was my supervisor, Mark, who was the postdoc before me in that project on the geological folding. Long time ago, he's now a professor at and some of my former researchers, so Levi and Jiao Shen, who were looking at thin wall structures, and Stelios, who was did later work on the sandwich panel. So some source articles. So all these papers have been mentioned in some way today, and just saying image acknowledgements is for the film. Okay, so thanks to Jürgen and to Gabriel and to Jessica for and that's it. Thank you very much.
You did indeed. And I never knew there was so much to do with buckling, good or bad. As Emma said, we have gone slightly over time, but we probably have time for just a couple of questions if everybody has a couple of quick ones. Anyone have a question? I just have one. Oh, thank you. You mentioned quite seemingly glibly that these things do deform into sine waves.
Yes.
A couple of those deformations didn't actually quite look like sine waves.
Wait, are you talking about the which ones? The ones in.
Well, something like the MATLAB thing you just flicked over.
Oh, right,
you
yes.
showed the beam. You said, well, your students right at the beginning were deforming a beam. You said that's a sine wave. It sort of didn't look.
Well, it's not quite a sine wave. If the local buckle is purely a local buckle, it would be a sine wave. But the thing is, it's bending as well. So the stresses are actually increasing towards the middle. So the middle one would actually be a modulated sine wave or a damped sine wave more than anything. So you have the maximum displacement in the middle, and you would be growing, and then diminishing again.
Okay. Just one more question, quick. Go on, Nick, and then we'll finish.
So when you talk about how different modes can be excited and such, so is there a rate dependency on that? So how quickly you load it depends on which mode would be excited.
Very, very good question. And it's not something I've looked at, but I know other people have. In particular for the cylinder, it's very much an issue. Okay, because there's so many modes kicking around for the cylinder. If you hit a cylinder, it may not trigger that mode. It may trigger a much higher mode. Because instantaneously the load is much higher than the actual static. What we're assuming here is everything is static. So we apply the load and we let it go.
Yep.
Apply the load a bit more and then stop. So the loading here is quasi-static, we'll assume. But if you hit something, then instantaneously that load may be something up here. Okay, and then up here you might be triggering much higher mode.
Yep.
That's why, for example, you stamp on a can, it doesn't trigger that mode, it probably triggers something much more messy.
Yeah. So yeah, I do a lot of impact modelling as part of my job, and one of the things that we concern ourselves with is which mode has been excited under this impact, because if you hit it harder, or quicker should I say, at a higher rate, then you'll excite a mode of higher frequency, which can cause different buckling. So,
Absolutely.
Yeah.
Absolutely.
Okay, thank you for that. And if I could just thank Emma one more time. Thank you. The next one, the next meeting is on the 20th.